Okay, we're continuing on in chapter 3. A lot of this is going to be review, but we're applying it to organic molecules, so you will see stuff that kind of looks new, but in general, it's just review of intermolecular forces. Let's recall, we've got a number of forces. Remember the van der Waals forces, sometimes called London forces or dispersion forces, instantaneous dipole, induced instantaneous dipole. These tend to be our weakest forces, and they come about from just the random movements of electrons that will induce small temporary dipole moments in the next molecule over in solution. And whenever you have two molecules that have polarity to them, the positive side of one molecule will attract the negative side of the next molecule over, and you'll get that force, that intermolecular force, attracting those two molecules. And although the van der Waals forces are the weakest in general, what we find if molecules have a large surface area, that increases the van der Waals force. So if we look at this molecule here, CH3, CH2, 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 CH3, 1, 2, 3, 4, 5, this 5-carbon molecule here, and compared to this 5-carbon molecule, we'll see this one has a larger surface area compared to this one. If you were to look at this carbon in the middle here and do a Lewis structure, you'd find that that's a tetrahedral carbon. So this molecule here is more like a ball. It's fairly spherical, whereas this is more like a snake. It is stretched out. So this molecule here can have lots of van der Waals forces with the next molecule over. If we say, okay, we line another one, CH3, CH2, 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 CH3, like this, we will find that we've got all sorts of places for van der Waals forces to occur, to attract these two molecules to each other. And because of that, there's a stronger force, intermolecular force, between these two molecules. And as we get to physical properties, that means higher boiling point. This one is more like a ball, a sphere, and when two spheres come in contact with each other, they only come in contact with each other really at one point right here, and therefore there's less chance for intermolecular forces here, lower boiling point. All right. Dipole forces. Note most of organic molecules are slightly polar, but only slightly polar. Now we do have the polar functional groups, the carboxylic acid functional group, amine functional group, the OH on an alcohol, that functional group. Those are polar functional groups, which add some dipole interactions between, say, an alcohol molecule and water, or an alcohol molecule and the next alcohol molecule over in the solution. But in general, organic molecules have very low dipole forces. They're really not very polar molecules. Speaking of water and alcohols, they can do hydrogen bonding. Recall, hydrogen bonding is a particularly strong dipole force with any molecule that has an OH on it or an NH, and technically, yes, an FH, hydrogen bonded to fluorine, but that's the whole molecule. Whereas OH on a molecule means alcohol, and there's a whole bunch of different types of alcohols that can have hydrogen bonding. Okay, so let's look at these physical properties here. The first thing we mentioned is boiling point. Recall, in order to have a liquid boil, the molecule will be very close to each other in the liquid, kind of rolling around on each other. The intermolecular forces are still there, attracting those two molecules so much that they are in contact with each other. However, if we raise the temperature enough, we can get the solution or this substance to boil. This liquid will boil, which means the two molecules that are close to each other are now going to be pulled far away from each other, which means we have broken the intermolecular forces. Boiling point is a great way to look at how strong intermolecular forces are. Okay. So, for example, water, H2O, has a boiling point of 100 degrees Celsius. That's a fairly high boiling point. Strong intermolecular forces, hydrogen bonding. Lots of hydrogen bonding in water that gives us a high boiling point. Ethanol, CH3, CH2OH, also has hydrogen bonding, but it boils at about 76 degrees Celsius. So it has a lower boiling point, which tells us the intermolecular forces in ethanol are not as strong as the intermolecular forces in water. Okay, but let's look at this a little more. The more electrons a molecule has means the stronger its van der Waals forces. We already looked at the surface area. Larger surface area means a higher boiling point because more intermolecular forces compared to spherical. But also the more electrons it has, the larger its polarizability. The ability of a molecule to become polarized, meaning molecules that don't hold their electrons very tightly are more likely to be polarized and therefore have stronger van der Waals forces. For example, CH3F versus CH3I. CH3 has a higher boiling point. Fluorine really holds on to its electrons very, very tightly. It's a small atom. The smaller the atom, the more it holds on to its valence electrons, the tighter. Iodine is a very large atom, so this iodine has many more electrons and it doesn't hold on to them as tightly. The larger the atom, the less tightly it holds on. So this is more polarizable. Iodine is a much more polarizable atom, which means it allows itself to be polarized. And recall, our dispersion forces are temporary forces, temporary dipole forces that come about when a molecule polarizes, induces a dipole moment in the next molecule over. CH3I very easily, this iodide very easily can be induced into a temporary instantaneous polar state. It's got larger polarizability due to the fact it doesn't hold those electrons very tightly. Okay. Now, another intermolecular force to look at, or another, physical property is melting point, and melting point can parallel boiling point, but there are some distances. In general, to melt a molecule, you must overcome the forces in the ordered crystalline solid. So, stronger intermolecular forces tend to mean an increase in melting point. Ionic compounds, very strong ion-ion forces, very strong intermolecular forces, high melting points. But we have to look at something else too. Given the same functional group and given roughly the same number of carbons in your molecule, the more symmetrical the molecule is, the higher the melting point. Now, we must look at what we mean by more symmetrical. I'm sure you're all chemistry majors and are going to take advanced inorganic chemistry your senior year, and you'll learn about molecular symmetry even more. And what you find out is what you consider symmetrical isn't always the most symmetrical of things. For example, let's look at these two molecules right up here. 1, 2, 3, 4, 5 carbons here. 1, 2, 3, 5 carbons here. So same number of carbons. They're both alkanes. Which is more symmetrical? This guy right here or this one right here? It turns out this one is more symmetrical. A tetrahedral molecule is more symmetrical. Although this looks nice and symmetrical. In the world of symmetry, this molecule doesn't have a whole lot of symmetry to it. This molecule, this tetrahedral molecule, has a heck of a lot more symmetry than this linear molecule. So, the way to remember it, the larger the surface area, the more spread out, the more linear the molecule. That means the less symmetrical it is. The more ball-like the molecule, the more branches off of a carbon, the more symmetrical it is. All right. And so we have this issue, interesting issue right here. If we look at this molecule, isoprene, both these two molecules have the same number of carbons and the same number of hydrogens. They are isomers of each other. Which is more symmetrical? Well, it turns out this one down here is more symmetrical than this one here. Since it's more symmetrical, it is more ball-like. More symmetricals have higher melting points. So we'd expect this one to have a higher melting point than this one, and it does. This neopentane here, the more symmetrical, melts at minus 17 degrees Celsius. The less symmetrical melts at minus 60 degrees Celsius. More symmetrical means it fits into a crystalline solid much better. All right. More linear, this one looks a little bit more linear, means it does not fit into the crystalline solid as nicely, and therefore it melts at a lower temperature. The way I like to think of it, grapefruit and oranges are very symmetrical, and so if you're at a grocery store, you can see stacks of grapefruit, and they stack very nicely. They're very symmetrical, so they stack really well. So they stack really nicely, and they're stacked so well that it's tough to just break one of them off, and it's tough to get them moving around. Very symmetrical. They want to hold that crystalline solid. They want to hold their position. Whereas molecules that like this look more like snakes. Have you ever tried to pile a bunch of like fake rubber snakes and try to make a pile of them? You can't make a very good pile of fake rubber snakes. They just don't want to stack very nicely. If they don't want to stack very nicely, it's more easily to get them rolling around off of each other, and therefore they melt at a lower temperature. It doesn't take as much energy to get the pile of rubber snakes to be moving around each other, or molecules like this. So the more snake-like, the less symmetrical, the more linear the molecule, the lower the melting point, because it's tough to stack snakes. The more symmetrical, the more ball-like, the higher the melting point, because it's easy to stack them. Note, this is for given the same functional group and more or less the same number of carbon atoms. And note, this is different from boiling point, because the more symmetrical it is, the lower its boiling point, because it doesn't touch it, only touches at a few positions. So although this neopentane has a higher melting point because it's more ball-like, more symmetrical, and stacks well, it has a lower boiling point because it is more ball-like and can't attract the ones next to it nearly as well. Isopentane has a lower melting point because it's more snake-like and doesn't stack well, but it has a higher boiling point because it has larger surface area, more intermolecular force attraction at different spots. Okay. And then let's finish up this chapter. The last intermolecular force to look at is solubility. Recall the old like dissolves like from general chemistry. Ionic compounds do not dissolve well in organic solvents. As we said before, organic molecules tend to be non-polar, or only slightly polar. So ionic compounds, the epitome of polarity, do not dissolve well in organic solvents. Organic compounds do not dissolve well in water. Yeah, they've got different polarity. Organic compounds, non-polar. Water, polar. But note, we talked about there are functional groups that are polar, such as OH and carboxylic acid, C double bond O, OH. If you have a polar functional group, then this molecule might dissolve in water. The polar functional group, we call that the hydrophilic part of the molecule. Likes water. Hydrophilic, likes water. The carbon chain, all of the carbons and CH groups in there, we call that hydrophobic, does not like water. So if we take methanol, CH3OH, hopefully you found in lab that dissolves in water really nicely. We've got the polar OH, although CH3 isn't that polar, this carbon-oxygen bond is pretty polar. It's a fairly polar molecule. But let's look at this one, CH3, CH2, 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 CH2OH. 1, 2, 3, 4, 5. 5 carbons in an OH. Is this water soluble? Will this dissolve in water, this 1-pentanol? Well, here's the deal. We've got the OH, that's hydrophilic, that likes water. But this tail here does not like water. Well, the tail here for this one, 1, 2, 3, 4, 5. So this does not want to dissolve in water very well because the hydrophobic part, the tail, the organic tail part of it, does not like the water. Only this end likes the water. And we have a general rule. For every 5 carbons per hydrophilic functional group, for every 5 carbons per polar functional group, if that's the case, the 5 carbons are less per polar functional group, it will dissolve in water. CH3OH has 1 functional group, 1 carbon, so that's less than 5 carbons per functional group, it will dissolve in water. 1, 2, 3, 4, 5. 5 carbons here, 1 functional group. That's right on the borderline. So pentanol, this guy right here, we're going to say is water soluble, but I'm going to put a question mark there because it's just barely water soluble. It does not dissolve that well in water, but will dissolve in water. This molecule down here, 1, 2, 3, 4, 5, 6, 6 carbons. We're going to say this is not water soluble. More than 5 carbons per functional group. And something to realize when we're dealing with our functional groups. Let's look at this molecule, 1, 2, 3, 4, 5, 6. A carboxylic acid is 1 functional group. Yes, we've got this polar part here and this polar part here, but this is 1 functional group. 1 functional group. Yeah. So will this dissolve in water? Well, there's our polar functional group. 1, 2, 3, 4, 5, 6. This is probably not that water soluble. 6 carbons, 1 polar functional group. If we had to go by yes or no, is it soluble in water? I would say no. Truth is, it's ever so slightly soluble in water. Of course, we learned in lab, though, if it's a carboxylic acid, what would happen if you added sodium hydroxide and gotten rid of this hydrogen right here to make this carboxylate group? Well, you'd make it an ionic compound, and then it will be soluble in water. Something very important to remember, that carboxylic acids that won't dissolve in water can be made to dissolve in water by adding base. All right. And other molecules to look at. If we have this molecule here, CH3, C double bond O, CH3, acetone, we note that 1, 2, 3 carbons, C double bond O, that's a polar functional group. We expect it to be soluble in water. It is. Turns out acetone is also soluble in carbon tetrachloride, a nonpolar solvent. Acetone, as we found in lab, dissolves everything. It dissolves in water, dissolves nonpolar stuff. It's just a really good solvent. 1, 2, 3, diethyl ether here. 1 group, 1, 2, 3, 4 carbons. We call it water soluble, but we actually used it in lab. It's not very water soluble. It's really not that water soluble. However, it's soluble enough that you have to add drying agents when you deal with ether, even though you do form 2 layers. Here's vitamin A, retinol. We can see we've got 1 polar functional group here. Double bonds are not polar. It's a carbon. A carbon bonded to a carbon, same electronegativity value, not polar. So we got a whole bunch of carbons, only 1 polar group. Vitamin A is not water soluble. Here's ascorbic acid, vitamin C. Oh, 1, 2, 3, 4, 5. Nope. This is our ester group right here. O, single bonded to a carbon that's double bonded to an oxygen. This is the ester group. So that's 1 functional group, 2, 3, 4, 5 functional groups. 1, 2, 3, 4, 5, 6 carbons. We almost have 1 polar functional group per carbon. So yeah, this is definitely water soluble. Vitamin C, ascorbic acid, is water soluble. All right, this ends chapter 3. If you're following along in the videos, we're now going to go to Chapter 2, Acids and Bases, and good news, a lot of that is review also.